In this session, let us see rotor fed induction motor. Okay, basically we don't have any application as of now in rotor fed induction motor in practical sense, but from examination point of view it is very important. Okay, like long back, prior to proper development of power electronics and drives, we used to have scratch induction motor. Okay, scratch induction motor we used to use for speed control of induction motor. So in that, we used to have rotor fed induction motor, but nowadays you don't find rotor fed induction motor anywhere. Okay, so rotor fed in the sense we are going to feed the supply to rotor. Okay, this is very important from examination point of view. Rotor fed induction motor. In rotor fed induction motor, this is rotor. In the rotor, we are going to have three phases: A, B, C. Okay. So for the rotor, how to feed to the rotor? We should have three slip rings. Okay, so this A will be connected to here, B will be connected to here, B will be connected to here, C will be connected to here, and we are going to have three brushes, and we will supply to A, B, C at rated voltage, rated frequency, for example. In the sense, 50 Hz supply will be given to the rotor. 50 Hz supply will be given to the rotor. Okay, now let us think of stator. In stator, you are going to have many conductors. Now, let me tell you about one thing. In synchronous also, I told you, in rotor, mechanical stress will be more because of centrifugal forces and all. The moment mechanical stresses are more, automatically in order to bear that hard composition materials like asbestos and all, we have to use. Okay, so if I keep the armature and the stator, what are the advantages? That much mechanical stress will not be there. So, low quality insulating materials like impregnated paper and all can be used. Okay, so point here is very simple. For example, if you think of squirrel cage rotor, okay, squirrel cage rotor structure will be like this. Okay, squirrel cage rotor structure will be like this. Okay, so how squirrel cage will be framed? Directly we are going to, for example, this is the rotor, we are going to punch the holes. Okay, and we will tilt it directly. Molten metal directly we can pour, automatically along with the end rings it can be formed. How much rugged it will be? Yes. Okay, so for example, if you think of squirrel cage induction motor, basically in rotating machines, most rugged machine is squirrel cage induction motor. Okay, most rugged. Actually, one thing let me tell you, in my practical sense, okay, normally, most probably, if induction motor is not rotating, in single phase induction motor, you have to check the capacitor, in capacitor start and run, something like that. Okay, in three phase induction motor, if rotor is not rotating, normally in practical way, directly you will check the bearings. Okay, so because electrically it is that much rugged. Okay, so such that for the motor normally nothing will happen. Okay, so for example, see here. Okay, means the moment in rotor fed induction motor, what are the disadvantages? For example, if I think of squirrel cage rotor, how much insulation we have to use in the rotor? No insulation. Directly punch the holes and pour the molten metal such that automatically it will be formed. But if you think of stator, phase A, phase B, phase C should be placed, and that too, distributed winding should be used, short pitch winding should be used. Okay, so because of this, means in order to form this, insulation has to be used or not? Yes. Okay, for example, if I keep that stator in rotor fed induction motor, that much great insulation has to be used, which is rotating, so mechanical stress and cost of the machine is going to be high. Okay, so that's why normally rotor fed induction motor we don't use, but they will ask in exam. Okay, so see here, for example, if I have fixed frequency with respect to the rotor, now my poles will be formed, N pole and S pole will be formed, which will be rotating at a fixed synchronous speed or not, ns or omega s. Okay, because the moment very simple, frequency is fixed, so means 120 f by p. Okay, so number of poles anyway will be constant. 120 is constant. So frequency, if you are supplying constant frequency, means that my speed of the what is RMF with respect to that particular part of the material is going to be constant. Okay, if frequency is reduced, synchronous speed will be reduced. 120 F by P, Ns is directly proportional to frequency. Getting my point, right? Now, what is what are the things we learned from stator fed induction motor? Okay, from stator fed induction motor, always my RMF was rotating at a constant speed with respect to stator. But what about the rotor frequency? Rotor frequency, if I strongly hold the rotor not to rotate, means stator frequency equal to rotor frequency at standstill. But if I release this, my rotor frequencies are going to be reduced till if my rotor is rotating at synchronous speed, my frequency of rotor is going to be 0. Okay, so let us apply the same thing here. For example, if I strongly hold the rotor not to rotate, rotor frequency is anyway constant. Previously stator will become now rotor, previously rotor will become now stator. That's it. Now if I strongly rotate the rotor not to rotate, frequency for example 50 Hz. So means if I supply one cycle voltage, one cycle currents, one rotation RMF, such that back EMF will be one rotation, one cycle. So if I strongly hold the rotor not to rotate, frequency of this and frequency of this will be same. Now if I release this, in which direction rotor has to rotate is the primary thing. Okay, for example, very simple. If if my earth is stable, if I move like this, I'm moving forward. Okay, for example, if I try to do the same on treadmill, then I will become stable. So treadmill belt will go back. Okay, so simple, if RMF is rotating in this direction, my rotor has to rotate in opposite direction with NR. Okay, actually people will not understand as of now, gradually you will understand. Let me draw it again. Okay, so for example, this is going to be, red is going to be the stator. Okay, stator, which is having many conductors of squirrel cage. Okay, for example, this is the rotor. In rotor, A, B, C are there. A, B, C are there, for which this speed is going to be N, S, poles. This speed is going to be fixed because operating frequencies are fixed here. Okay, now see here, for example, if I sit here, please sit here. Okay, so if I strongly rotate, stop the rotor not to rotate, speed of rotation of this with respect to rotor equal to this. So if 50 Hz frequency is induced here, because supply frequency is 50 Hz, so induced voltage will be 50 Hz, the same frequency will be induced here because rotor is not rotating. Now for example, if I leave the rotor, what should be the frequency of here? It should be reduced or increased? It should be reduced. And if at all, if the rotor is being rotated at synchronous speed, frequency of induced voltage should be 0 here. Okay, now simple, for example, this is my hand. Okay, so this is my hand. Okay, in this hand, okay, this is going to be my rotor. Okay, so let us see, this is the stator. On stator you are sitting here, and this is my rotor pole. This is rotor pole, this is my hand is my rotor. Now for example, upon rotor my rotor pole is there. Okay, so for example, my rotor poles are rotating with respect to rotor in this direction. My rotor poles are rotated in this direction with respect to rotor. Okay, for example, let us assume that rotor is rotating at synchronous speed. If rotor is rotating at synchronous speed, how much should be the frequency of induced voltage or magnitude of induced voltage? 0. Okay, so for example, see here, this is my rotor. Okay, so just a minute. This is my rotor. Okay, this is my rotor. Upon the rotor, my rotor poles are there. For example, my rotor is rotating with synchronous speed. Okay, so rotor is rotating with synchronous speed in this direction. My rotor poles are rotating in this direction with synchronous speed. Okay, hope you are getting my point. For example, let us assume that my rotor is rotating with synchronous speed. Okay, so this is my rotor. This is my pole. Upon that, rotor pole is there. So with respect to rotor pole will rotate with constant speed of ns. Okay, so for example, with rotor is rotating at synchronous speed, means that if rotor pole is rotating in this direction with synchronous speed, if rotor is rotating in this direction with synchronous speed, if you sit here, your induced voltage will be 0 or not? Yes. Okay, let me repeat again, relax. Okay, so for example, see here, rotor pole, rotor is here, rotor is my hand, rotor pole is here. My rotor pole is rotating in this direction by 90 degrees. By 90 degrees. By the time rotor pole is rotated in this direction by 90 degrees, if rotor rotate in this direction by 90 degrees, okay, so you will always see my N pole only or not. For example, this is N pole. Okay, so if my rotor is rotated at synchronous speed, induced voltage in the stator should be 0. Okay, so see here, if my rotor pole is rotated in this direction, by that angle rotor is rotated in this direction, always you will see N pole only. Under that condition, rotor stator induced voltage will be 0 only. So very simple. What is that? Like, you know, rotor direction of rotation should be against to the RMF, direction of RMF. Okay, so for example, see, if it is, this is rotor pole, if it is rotating in this direction, and if you feel rotor also will rotate in the same direction, under that condition, this velocity plus this velocity is going to be 2 times velocity. Okay, if rotor is rotated at synchronous speed, under that condition, how much will be the frequency of induced voltage in the stator? Is going to be 2F, but it should be 0. So if rotor pole is rotated in this direction, by the time rotor rotate in opposite direction, induced voltage in the stator will be 0, frequency will be 0. Getting my point, right? So rotor has to be rotated against to the synchronous speed. Forget about it. Now, from previous session of stator fed induction motor, what do we know? Means stator MMF and rotor MMF should be stationary in space, so they have to rotate at the same speed. Okay, now the same thing will happen here also, but stator there became rotor here, rotor there became stator here. Okay, so let us see relative velocities. Okay, so relative velocity between stator MMF and rotor MMF should be 0, otherwise continuous electromagnetic torque is not possible. Okay, now let us think of, you need not analyze much, not at all required. Okay, if they ask you with respect to stator, sit in the stator. If they ask you with respect to rotor, sit in the rotor. For example, relative velocity between stator and rotor MMF. Okay, stator and rotor MMF. Why do you think of rotor MMF? Because stator MMF and rotor MMF should be stationary in space. So stator and rotor MMF, forget about rotor MMF, because rotor MMF and stator MMF rotate at the same speed. No, keep stator MMF. Stator and stator MMF. See, stator and stator MMF. What is the frequency of stator once it starts rotating? It should be slip times frequency. Okay, so see here, the moment rotor is supplied with fixed frequency of 50 Hz, induced voltages here should be 50 Hz only. But once rotor starts rotating in the stator, frequency should be SF. Okay, so relative velocity between stator, or see here, stator. Okay, so relative velocity between stator and stator MMF is going to be S omega S, because frequency is SF. Okay, now relative velocity between rotor and stator MMF. Forget about stator MMF. Basically, in this question, you are sitting on the rotor. So, if you sit on the rotor to rotor MMF means, let us think of rotor frequency. Rotor frequency is rated frequency. Rotor frequency is rated frequency of FR, 50 Hz or not? Yes. So, the moment supply frequency is constant at 50 Hz, automatically back induced EMF frequency should be same. Means that with respect to that, my MMF should rotate with NS. Okay. So, rotor MMF with respect to rotor, in the sense rotor frequencies are fixed at 50 Hz because we are supplying 50 Hz to rotor. So, it is going to be omega S. Okay, so simple, relax. Simple. The logic is very simple. What is that? Basically, relative velocity between stator MMF and rotor MMF should be 0. Okay, and in rotor fed induction motor, rotor rotate against to the direction of RMF. against to the direction of RMF. Second. And third thing is relative velocity between stator MMF and rotor. Forget about stator MMF. Keep rotor MMF, sit in rotor. Rotor and rotor MMF. Frequency of rotor is constant, F. So omega S. Forget about it. For example, relative velocity of rotor MMF with respect to stator. Forget about rotor MMF. Keep stator MMF. Now stator and stator MMF. What are stator frequencies? S into F. So S into omega S. Okay, so actually if few people are unable to understand, just repeat it. Okay, means repeat the video such that definitely you will understand second time or third time.